Good morning to everyone. This is a special opportunity for us at IMPA to receive Professor Giuseppe Mussardo from the Scuola Internazionale di Studi Avanzati, SISSA, in Italy. Professor Mussardo is a well-known specialist in statistical mechanics and mathematical physics. He has been to Brazil a few times. He's part of the board of directors of the International Institute of Physics in Natal. And today, Professor Mussardo is going to give a very interesting talk on a subject that's extremely dear and important to us, the subject of Riemann hypothesis. So, Professor Mussardo, thank you very much for being here.
Thank you very much. I'm really very pleased and honored to visit IMPA, great institute, great place. And today I would like to talk about a problem which has fascinated mathematics since long. And I'm going to present you a physicist approach, statistical physicist approach to this old problem. So let me say that someone come to you and say, look, I discover a function which in the complex plane has all zeros on the line 1/2. They'll say, wow, this should be something really incredible that. And then someone say, well, this is the Riemann function, connection with prime numbers, so you might start getting suspicious that something is going there quite deeply. But then imagine that another one come and say, look, I discover another function which has also 0 on the line 1/2. Then another one comes, another function, 0 on the line 1/2. Another one, another one, another one. Infinitely many functions as the zeros on the line 1/2. Well, at that point, you start suspect that something's going on which has to be universal character. Cannot depend really on the detail of how these functions are built on. So this is what I would like to convince you today, that the fact that many of these functions, which I will define properly later, as always zeros on the line 1/2, has to do with random walk. And namely, the growth of random walk up to log correction, that will become important later, but the leading singularity, the leading exponents of the random walk is what will explain while infinitely many functions will have 0 exactly on that line. So this is the message to take home, namely there is some random walk process behind all these functions which are called Dirichlet functions, out of which Riemann is just one specific example. So on these topics have been devoted a couple of papers with André Leclerc, and another one is on the way. And about the topics of the seminar, I will spend a reasonable amount of time on the art of counting, namely making even an historical background what the problem is and why Riemann was interested. Then I will be really seduced by the zeros and all the phenomenology which is behind. Then we take another route and start talking about arithmetic progressions and introducing Dirichlet character, L-function and all that. And we will see that there is really the grand picture behind this story, which is not only Riemann, but really concerning all the Dirichlet function. And this goes under the name of Generalized Riemann Hypothesis. And then we'll really touch very deep, in my opinion, topics, which is really the tension which always exists between randomness and determinism. And we will see that this is a lot to do with the problem today. So Riemann, as you probably know, was born in one of the poorest regions of Germany, was a son of Lutheran minister, and was supposed to become minister as well. However, he went to Göttingen and came across Gauss, and this changed completely his life. So he made the PhD with Gauss, really introducing the complex analysis as we know, then went to Berlin, And then in the 1857 come back to Berlin, and in 1859 was his annus mirabilis, because he became professor there and was elected member of the Berlin Academy of Science. And in that occasion, he has to deliver a paper. And he decided to deliver a paper about number theory, the only one he made on number theory, which is on the number of primes below a certain magnitude. And so this is the manuscript of that paper, which has really changed the mathematics since long. Now, if you go to the page 3 of this paper, there is this famous sentence. It's very probable that they are all along this line. Of course, it would be desirable to have a rigorous proof of that, but after a few vain attempts, I leave the problem apart because this seems unnecessary for the next objective of my investigation. He's talking about the zeros. As a matter of fact, it has been discovered later that he has elaborated what has become Riemann-Siegel formula, that is a way of computing the zeros, and he has probably computed 1, 2, 3 of them, always find that they were aligned. So this is bring him to this famous conjecture. Now, the Riemann hypothesis and the generalized Riemann hypothesis is indeed one of the most important problems of the last 150 years. And I have to say, and I have to stress, which has completely different status of other important and famous problems in mathematics, like the Fermat last theorem, of which we know that the solution is taking very, very long. However, the Fermat theorem is, mathematically speaking, sterile. How to say, once you prove it, what will come out from it? Nothing. A lot of mathematics has been developed to solve the problem, but nothing come out from the validity, or in this case, the non-validity of the Fermat theorem. Now, completely different status for the Riemann, because the entire monument of mathematics is based on the Riemann hypothesis. So many, many theorems say, assuming Riemann hypothesis, then you get something. So distribution of primes, for instance, large gap or distribution of gaps, growth of other arithmetic function, zoo, there is a zoo really of zeta function. There is quantum mechanics and primality test that you can base on it. Random matrices connection is very deep together with all the relation of quantum chaos. And also general theory of phase transition, because the so-called Young-Lee zeros, which are special zeros of partition function, is as much as the zeros of this function, which can be considered as partition function, as I will discuss in a minute. Now, on the topics, there are beautiful books, of course. It's a classic. So Edwards is one of the best, also has some very interesting historical part. I like also very much this collection of problem and comments, which is in these other books. Now, everything starts, let me just go now on the historical part, because this is very, very interesting what is the background and really what is behind all this and why Riemann was interested in that. Now, the problem is counting the prime. So, historically, pi of x denotes the number of prime less or equal a certain amount. Now, this function, of course, is a staircase function. So, as a jump of 1 each time you met a new prime. And the prime itself, just the inverse of this function at the value 10, let's say. So the inverse is the 10th prime. Now, of course, when you have a function like this, it's a question of scale, how you are going to look this function. So on this scale, you see very, very clearly the stairs. However, if I start plotting on a larger, larger, larger scale, you will see that this function is tending, is going, quotation, to some smooth function. So the problem is, what kind of function is this? Now, this has attracted the interest of young Gauss. He was 17 years old, and was curious really to count the prime, and he did it. And he arrived to an estimate of this function, which is the logarithmic integral. Now, it's very interesting how you can get this law with very, very simple assumption, and the line is this. You have to assume there are no correlation between prime numbers. It's not true. There are small correlations. but let's say first approximation, no correlations. And 1 over p, of course, is the probability that any given number is divisible by a prime p. At this point, if you want to know that x is not a prime, you have to multiply all the probability that this number is not divisible by 2, by 3, by 5, up to, let's say, square root of x. So this is the probability that the number x is not a prime. Now, dealing with product typically is difficult, but if you take the log, this becomes a sum. 1 over p is already larger than 1 or less than 1, so you can develop. At this point, there is the coup de théâtre. The coup de théâtre is that you are summing on prime, but you can convert this sum on integer with the probability that the integer is a prime. So involving the same function you're looking for. At this point, it becomes very simple to take a differential right and left and get a differential equations. And this differential equation, the solution is simply 1 over log. Okay? Simple like that. Now, of course, the story is a little more articulate and richer, is what I'm going to. But this is the way to understand broadly from a physicist, let's say, point of view, how the prime is, what the prime is about. Now, keep in mind that prime are rare, but after all, not so rare. For instance, the probability or distribution of prime leads is this, but if you think what are the distribution of a square, is much, much less. So there are much less square than primes. Now, if you take this estimate of the function, you see that the error you are doing essentially is like the square of the value itself. Just counting the digit here. So you are making really a big mistake going higher. So Riemann's question was, can I do something better? Can I really improve this estimate? So at this point, he considered the Riemann zeta function, which was already known before him. Euler proved this beautiful identity concerning this function as a series together with product on primes. And the proof related just on the fact that any integer number has one and only one decomposition in terms of primes. Now, from a physicist's point of view, this identity is very, very suggestive because is just an identity concerning partition function of bosonic particle. Namely, let me assume that there are bosonic system. Bosonic system means that you can take particle on the same states how many times you want, and then I give them a very special dispersion relation. Namely, the energy of this particle is labeled by the logarithmic of the prime. Now, if I have these levels and beam bosons, I can populate them as much as I want. At this point, this identity of Euler is nothing else than an identity of ensemble of statistical mechanics. On the left-hand side, there is the grand canonical ensemble. On the right-hand side, there is the microcanonical ensemble. And these are known to be true, identities which are known to be true, and give us a different interpretation because the parameter S is nothing else than the inverse of the temperature. At this point, in the complex plane, this partition function blows up to S equal 1, that from a physicist's point of view is called Hagedorn temperature, means the density of states grows so fast that at a certain point the system cannot sustain any longer this growth, and there is a pole. So these partition functions are intrinsically defined in low temperature phase. And the question is, what is the system in high temperature phase? Well, Riemann, after all, was the master of analytic continuation. He invented. So he just find a proper representation of this function which allows to go in the forbidden region. And in this way, he found the famous functional equations which related the value of the Riemann function for S larger than 1 to S less than 1. containing trigonometric function and gamma function, you can immediately read where this function has zeros in the complex plane. And there are zeros which are really certain, are just the zero of the sinus that was there. And Riemann was talking about these other zeros, which in his opinion and his conjecture were all aligned on the line 1/2. Now, the functional equation of Riemann has a very weak, well, is a strong but weak information on these zeros, because it tells us that if there is a zero slightly displayed up, there is another zero slightly displayed on the left, and vice versa if it's the other way around. But doesn't imply that they have all to be on the line 1/2. Okay? Now, what are the connections between prime and Riemann zeta function? Well, these are just a few lines of derivation, which, by the way, is in Edwards' book, and is exactly the same steps that Riemann took it. So you take this identity for real part of S larger than 1. You take the sum of the log. At this point, as I did before, you introduce the function pi of n, which count the prime, and then you convert this sum on the prime on sum on integers. Then, being an infinite series, you just make a shift, and you just go in the difference of the log, not the difference of the function. And at this point, you express this as an integral. And being pi of n constant between n and n plus 1, you can bring it in. At this point, you have this identity, which is just this. So Riemann found this beautiful formula that says the logarithmic of the zeta function contain information on the density of prime. And it's about kind of Mellin transform. This becomes very clear if you really make a change of variable, and you express this really as a Mellin transform of a function which is this Js, which is a series of the function pi computed in all the higher roots of this x. Now keep in mind that this is not a series, it's finite, because given any x, taking enough power, root, you get less than 1, but less than 1 is 0, pi of 0 is 0, okay? So this is not a series, it's a finite sum. So we have to invert these things. So this is how this J function looks now as a discontinuity in all the fraction. And he has to invert this series, and this is done through a trick which involves Möbius. So indeed, Riemann made this inversion, which involved the Möbius coefficients, which are 1 if the integer doesn't contain more than a single prime, and depending the parity, how many primes you have, -1 the same, and then if the number contains more than twice the same prime is 0. From a physicist's point of view, this function is really fermionic function, because just count how many different primes you have and how many of them, and there is a parity in it. There is a very interesting story concerning this function itself, but I do not have time now to talk about this. So this function has the Mellin inverse, and therefore, evaluating this, Riemann got this famous result that the first approximation of the J is the logarithmic integral. Then if you want to be more precise, you have to compute this to the zeros of the Riemann function, and then there is some finite part. Now, bringing all together, you get that this function which count the prime contain a smooth part, which now is this series. And if you go and get and see how these perform better, you see that perform much better than before. Not only, but while before was only from above, now is oscillating. Indeed, the difference is like a random function oscillating around zeros. So this is what has been dubbed the music of the primes. I think it is due to Michael Berry. The fact that you have some frequencies behind which are somehow related to the primes. So the problem is you have a function which grows that now you control very, very well, and then some oscillation around it. And then you do Fourier transform. Okay? So the function you are looking for contains a smooth part and this part which is the oscillating, which indeed the frequency are just the imaginary part of these zeros. If you are curious to see how the things work in detail, this was the original function. So the smooth part just passed by all the stairs, but then you are more ambitious. You want the function. And therefore, you start adding frequencies like Fourier transform. And more you add, more you get closer. Okay? So this is the story in a nutshell. So the zeros of the Riemann function concern with this oscillation part. Now, summary of this part, Riemann function has to do with the counting of primes, and if Riemann hypothesis is true, one can have a very clear estimate of the error that you are doing each time that you consider this. Now, the number of zeros in the critical strip. This, there is a way of counting the number of zeros without even knowing where they are, because you just use contour integral, and this was done really by Riemann itself and then making more refined by von Mangold. So we know that there are many, many zeros, and their number grows like t log of t, where t is the height. So out of this, the message is we know there are zeros and there are infinitely many in this strip. By the way, this is the way how people check they are counting the zeros properly, because they compute it, match with this formula, and then if they have all the zeros they need, they know that there are no others in top of that. So many people have been seduced by computing these zeros. The first was Riemann itself, but many, many others. And notice that was also Turing. Turing didn't believe to the Riemann hypothesis and actually computed itself, his mechanical computer, to compute the zeros. And with his great surprises, he computed 100,104, and all of them were alive. Okay? So this was just 1 year before he died. And nowadays, this has become really kind of Olympic of finding the zeros for certain reason. There is an interest di per se, as the first man who went to Everest replied and said, why you were there? I mean, was there, I want to go there. So, I mean, here people are interested to compute them, but there is something more than sport. And this has to do, really, with a very amazing conjecture between random matrices and zeros of the Riemann function. Now, the story goes that in Princeton, there were Montgomery here that was working really on the zeros of the Riemann function, and Odrinko has been one that is making really a great computer, a great number of them. And then at T time, he met Dyson. And then Dyson said, so what are you working on? Montgomery was very young. He said, well, I'm studying the zeros, and I found really some very funny correlation. And Dyson said, I think the correlation is 1 minus sinus squared divided x squared. And Montgomery was stunned. And indeed, checking the story came out to be true. So let me tell what Dyson say, what Montgomery discovered together. So if you parameterize the zeros in terms of real part 1/2 plus the imaginary part, and you consider what a physicist calls gap, namely you promote T kappa to be eigenvalues of something. So you consider the gap between the two next eigenvalues, but then this guy better to normalize to the average in some way that the system looks in average like an harmonic oscillator. Okay? At this point, you are sensitive to fluctuations. And when you go and see the distribution of this gap, you find a beautiful match with the Gaussian unitary ensemble. And the correlation is this famous function, okay? That Dyson says straight away, the correlation has to be this. And then Montgomery went and see that indeed the zeros were aligned in that way. So fantastic, fantastic snapshot of the story. Now I have no more time to elaborate on that, but roughly speaking, the function has this zero, which however is as random as possible. As a matter of fact, there is also Voronin theorem, which says that the Riemann function is the most universal function you can think of, namely is able to simulate any function you give me. There is always a region in the critical strip where you find perfect match with the function you're looking for. Now, this is history, let's say, but mutatis mutandis, all the property that I've been telling you so far holds for infinite class of function known as Dirichlet L-function. So now I have to open another page of this book. First of all, we have to go back to Göttingen. Actually, all the stories relate to Göttingen in a way or another. Gauss was professor there, Riemann studied with him, Dirichlet became a professor in Göttingen after the death of Gauss, and so on and so forth. So I have really to introduce you another character, which is Legendre Dirichlet. One of the founders of analytic number theory. He studied in Berlin, but he has very strong connection with the Paris school at that time. He was very gifted in Fourier series that was started or developed at that time. And Dirichlet was interested in the following problem. He says, imagine I take an arithmetic progression made of two integers, q, which is called the modulus, and h, which is called the residue. Okay? So he asks, are there prime on these sequences? So what are the conditions on q and h such that the sequence contains infinitely number of primes? And amazingly enough, q and h must be coprime, so should not have a common divisor. This is not only necessary, of course, but Dirichlet proved to be necessary, sufficient. So it's sufficient and necessary. So just to give a few really examples for the sake of so if you take modulus 5 and residue 3, and you just make all this progression, you find many, many primes along the way. Another one, you find another primes along the way, and so on and so forth. Now, geometrically, you are just drawing parallel line with the same slope and different residue. Now, if you are an experimental mathematician, whatever this means, you just see how the prime goes on this line. So I'm just plotting all the various prime that you get it. And imagine that you just count along the line. You are curious to say how many there are on the line. You discover that in average they are the same number. Okay? Now this becomes important for what I'm saying you later. So what Dirichlet did was to introduce the notion of lattice on integer, like in physics. So you take the integers, but then using the modulus, you just organize them in periodicity. Okay? So you do what is called modular arithmetic, out of which Gauss was the master of it. Now, for the clock, say the modulus is 12, actually, not all the numbers are good for what I'm talking you later, but you need to select the primes, which are, the numbers, which are coprime with the modulus you have selected. So for 12, the only numbers which are coprime with 12 is 1, 5, 7, and 11. Why you need so? Because you want to put a group structure on it. Group structure, which is just a Abelian group structure, and you want to do multiplication modulus the modulus you have chosen. So in this way, with the number which are coprime, this is really a group. So you might wonder yourself, what's wrong with 2? Why I cannot use 2 or 8 or 4? The reason is that if you choose 2, 2 times 2 is 4, but as well 2 times 8 modulus 12 is also 4. So you have no inverse. So there is no group. So the only way you can define a group is restricting yourself to the coprime numbers. This is an abelian group. So the abelian group is called abelian group of prime residue class modulus Q, has a number of elements which has the Euler-Totian function, which is how many numbers are coprime less than the modulus Q. And that is a very well-known formula. So if you choose as a modulus a prime, the dimension, this group is just Q minus 1, because all the number less than the prime doesn't have any coprime with it. But if you choose a composite number like 20, you have to be careful, and you have to throw out all numbers which in this case divide 2 and 5. Okay? And the dimension in this case is 8. Okay, now, these are the basic of the game. So you have to do modular arithmetics. Now, on top of this, Dirichlet defined the characters. The characters are simply 1D representation of this abelian group. Now, general theory of group theory says the number of irreducible representation is equal to the number of classes. But for abelian group, the classes is equal to the number of elements. So we have exactly as many characters as the dimension of the group. Moreover, being one-dimensional representation, they can only be phases. So they can be only angle, associated to angle. And these arithmetic functions satisfy a series of very simple properties that I'm going just to simply recall. So there are pq different functions that you can assign if you give me a modulus. So the properties, they have to be periodic, because it's what I'm doing. Then Q of 1 is 1 and Q of 0 is 0. The function is purely multiplicative. So each time that the chi has of a product is the product of the character. Is 0 if you are hitting a number which is not coprime with the modulus. And moreover, when it's non-zero, the phi q power has to be 1, because it's just the rule of the group which is behind. So these phases has to be root of unity related to the modulus. So example, if I take q equals 7, all the character has to be built with the 6th root of unity. Okay? So I denoted omega this complex number. In this case, I'm going to have 6 different characters made of all this. Of course, there are beautiful relation, orthogonality, all the stuff which concern with group theory. Notice that there is always one character which contains all 1, is the principal one. So Riemann is just the principal character of q equal 2. Just a simple case of this example, but this is the most general theorem. Now, the Dirichlet L-functions are just some which involve now the character, and they have exactly a Euler infinite product formula, because this formula is simply based on the multiplicative property of the character, which I just used it before. It satisfies functional equation as much as Riemann, and there is a residue at 1. And here is the very interesting stuff. The interesting stuff is this function has a pole in 1 only if you concern with what I call principal character, namely all the one in which I choose the character to be 1. Because in this case, they sum it up and then make the divergences. But in all other cases, being a complex number which has as many positive as many negative value, when you sum up, there is the sum of the character which is 0. because it's an identity of the character. So the story is the generalized Riemann hypothesis, which appeared first in a paper by a mathematician Pils, 1884, says that the non-trivial zeros of all Dirichlet function, all means for any modulus and for any character, are all along the critical line, placed at line 1/2. Okay? Now you see that this character has a lot of details, a lot. But if the zero are all aligned on the line 1/2, these details should not matter, right? This is what a physicist would imply, and this is what I'm going to show you later. Now, for what the zeros are concerned, is necessary essentially to consider two different cases, namely the L function of principal character and the L function of non-principal character. This is a technical detail. Today, I would like to present how you can approach this conjecture for non-principal characters. It's it's technical problem, but let me tell you what the problem is. The problem is the L function of principal character, for what the zeros are concerned, is essentially equivalent to the Riemann function. And the reason is this Dirichlet function multiply the prime but those which divide the modulus. So what I can do is add and divide, add and divide. So at this point, all these Dirichlet function of principal character are proportional to Riemann with something which is never zero. So this means that if you prove for Riemann, you prove for all these functions and vice versa. Okay? But Riemann somehow is a harder case. I'm not going to discuss unless later you have curiosity. I will tell you what you can do. Today I would like to discuss non-principal cases. Why? All these functions are essentially on the same footing, infinitely many. And they share the same general property. Which are these property? They are entire function. There is no longer the pole. They have only zeros in the complex plane. Now, this is an amazing simplification. So this function is a pattern of zeros, but no pole whatsoever. So you will see in a minute why this is simplify a lot of the life. So this is really an enormous simplification to approach these things. Now, what I'm going to do is really use law of probability to go on. Okay? Why law of probability? I have to present you a very shocking theorem which is not well known in the community of mathematicians. The theorem is due to Grosswald and Schnitzer, is around 1945, and says, look, you think that all this is related to primes. You think. But this is a fake hint. You can take any sequence of random integer as far as they grow like the prime. But I can do whatever. I can make a sequence which grows like n log n with any integer I want. And at this point, construct your own Dirichlet function. This is my own definition once I select a random sequence of this number. At this point, the theorem of Grosswald and Schnitzer say this random function is purely random function has exactly the same zeros of the Dirichlet ones. The same, exactly the same. And the proof is stunning simply. The proof is, so this is an example. The blue one is the real one of the real Dirichlet, the modulus, I take them all. Here, I just generate a series of random numbers, and I plot it. I just generate, this was around probably 100 terms. You see that the function is random, but always pin where the zeros are. And more I included, more I pin down. So how it could be? Well, you take the Dirichlet function itself and the putative one, and you take the ratio. Now, this ratio says that as far as this term is non-zero, the zeros of this has to be the zeros of that. Okay? Simply like that. And this function is non-zero? Yes, it's non-zero. because the term is made of grows exactly the same way. And therefore, this infinite product has never zeros in the critical strip. Okay? So simply like this. So from this result, you understand the prime themselves has nothing to do with the zeros. I mean, it's a fake hint. It happens that they made it, but you can have for arbitrary sequence. So this opened the way to probabilistic approach to the generalized Riemann hypothesis, okay? Based essentially on this kind of ideas. So the main idea is we look to enlarge the domain of convergence of the infinite product entering in the strip. So what I mean is originally these functions were defined intrinsically on the right-hand side. I was stop s equal 1, but in this function there are no poles. So a priori I can get in. So the question is how far I can get in the critical strip, when I'm going to be stopped. So I need some diagnosis. I need some function which tell me, please stop here, you cannot go on. And the function is, if I take the Dirichlet function, I take the log. Now, the log of a function diverge if the function has either 0 or pole. But there are no poles in this function. There are only zeros. So this means that this is the indicator I'm going to use it, and each time this guy blows up, I'm stopped by the first zeros. Okay? So this is the idea. So the singularity of this function depends only on the zeros of the Dirichlet one. So I parameterize as usually complex value s like real part plus it. And then there is a little of massage. Namely, I take the original series infinite product. I use the character. Remember, key was exponential I theta. So you massage a little bit this log, and then you end up in this Mellin transform formula. So the log of this function, of the Dirichlet function, is a Mellin transform of a density which is made of frequency, which are the logarithmic of the prime, and the value of the character computed at the prime. Okay? Now, when you have a Mellin, the divergence of the Mellin is signaled by the power law of the density you are using. So if Bu grows asymptotically like n to alpha, alpha is indeed the point where this integral diverges, and therefore is the coordinate of the first zeros in the critical strip. Okay? So the situation is like this. Imagine you have a distribution of zeros. The zeros, the most on the right, has coordinate alpha. Alpha will be exactly equal to the growth of this function here. Okay? This is just the way the Mellin transform works. Therefore, if I'm going to prove or I show you that this density grows like square root of n, then all the zeros are on the critical line. Because I have also duality. So if I prove that one is on 1/2, the other has to be on 1/2. Since I know there are infinite remaining on the critical line, and I found nobody out of line, all of them has to be on the critical line. Okay? So this is the line of thought. So I have just to argue that this density grows exactly like square root of n. Now, keep in mind that if I have a violation of this scaling by logarithmic, this is never spoil my conclusion, because Mellin transform only depend essentially on power, but you can add any log you want. The singularity are always dictated by the power alone, with correction, which might depend on the log. But the pole depend only on the power. Okay? This is important because in any things of Riemann, there is always like zeros 1/2 plus epsilon. This epsilon stays for infinite series of log. Okay? So the large asymptotic behavior of this series, therefore, is the ideal diagnosis for the real part of the zeros. So let's look in detail at this series. This is the random series I'm talking about. So concerned with term which end up with the cosine of this angle. Now let me plot this function. It really looks random as you can imagine. It's not random. It's purely deterministic. But if you don't know where this is coming from, you can see immediately that looks like random one. Now you can convince yourself that something is going on there if you just make a naive histogram. And you find the histogram is exactly the distribution of cosine of a random angle. Okay? It's not a proof. I'm just playing with. This is the series itself. I'm summing this series, and this is how the series goes. Okay? For a given character. But if you change the character, it's always the same. So at this point, we have to rely really on a master of probability number theory. Well, rely at least for inspiration. So Mark Katz has been one that has really provided a lot of hints in number theory coming from probability. For instance, he established a theorem with Erdős that says, if I give you a number, what is the number of different prime is made of? Well, amazingly enough, it's log of n. So this means that if you give me an astronomical amount of astronomical large number, and you count how many prime there is on it, very few, like handful number of it. It's a theorem. So Mark Katz established a theorem, which is called Katz theorem, which says that if you take a purely deterministic series made of frequencies which has no common divisor, this purely deterministic series, as a matter of fact, satisfies normal law distribution. So if you say, what is the probability that this function is between these two values? Normal distributed. Okay? Now, this, unfortunately, is not what I need. But I'm just bringing you this attention to show you that the difference between determinism and randomness is very, very feeble. Very, very teeny. Okay? So, random walk. So I had the goal to show that this series goes like a random walk. Now, random walk, as you know, has three classes of universality. Namely, depending how the variance grows, let's say, with time. So you might have super diffusion, means this random walk goes too fast. You might have normal diffusion, which is what I need, and you might have subdiffusion. It just goes slowly. Now, let me tell you that while Brownian motion, to go far away, you need really to coherently add many, many, many points. You can have super diffusive behavior with what is called Levy flights. Levy flights is like the bird. The bird can make a big jump on another point, and then when they're right there, make a little random walk there. With Levy flight, you can have something which grows more than square root of n, because with only one jump, you are far off. But if you are in Brownian motion, to really get bigger, you really need to add one all positive or all negative. And this is very improbable, because since being equal probable, you need to have something which goes exponentially if you want to go. Okay? This is very crucial in the story. So now I have to analyze this sum. It's made of cosine of angle. What we know about this series? Let me just go one by one the property. Well, first of all terms are the same order. So I cannot have flight, Levy flight, because all of them are order 1. Okay? There is no a single term that is larger than the other one. Secondly, here is a beautiful theorem of Dirichlet. This is a theorem. Theorem of Dirichlet stated that all the angles that you are going to find along the sequence of prime are equiprobable. is exactly the number of dots I was counting on the straight line at the beginning. So essentially, I'm dealing with a dice. The residues are like dice. I have q minus 1 phases of these dice. And they are all equiprobable. Now, if you are a skeptic, as I was at the very beginning, I just count. I just made this and make a huge statistics to check also the translation invariance of this statement. Namely, if I'm going to check the distribution in a given segment of the prime, are they equidistributed? Yes, they are. And you find really beautiful data, which really in this case of Q7 converge relatively quickly to the value 1 over 6. And this is invariant all over the sequence of prime. Therefore, with these things, I have as many positive as many negative, all equiprobable. Therefore, a consequence is that the mean of this series has to vanish. It's a theorem based on Dirichlet. Okay? Now, to establish that this is a random walk, I do not only need they are equally distributed and plus and minus, but what is their correlations? Are they correlated? So this is what I ask myself, and I spend an entire winter in Utrecht playing like the Kepler game, namely spanning milliards of primes and checking this residue. Really like Kepler that was doing the orbits of the planet. I miss it Newton as Kepler was missed. But once I found it, I see the light. So what was about? I made the studies really statistically. So I take these values and compute, say, the correlations. I compute this correlation, and the correlation is stunning delta function. Essentially no correlation whatsoever. Okay? Now I zoom it, and there is non-zero, but really small. Now you convince yourself that really there are very, very teeny correlations if you do the Fourier transform. And if it was random completely, you should see flat stuff. It's not flat, but it's not wild either. Okay? So I have to quantify the deviation of this, and if this deviation is going to be important to spoil the random walk behavior. So then I discovered Newton, as I said. I discovered that R.D. Littlewood, and in more recent time, Olivier and Sundararajan has studied this correlation. And they found a formula. So the formula tells me what are the correlation if I get some residue theta A at the prime Pn, what is going to be the second one, the second residue to the next prime, or primes which differ by kappa steps. So they were really the Newton of the situation. They stated this law. Now, I made my experimental mathematics without knowing Newton, and find that this probability made a probabilistic process which was not Markov. Namely, if I knew the probability of the next, if I want to go to the kappa, it's not the product. They were the correlation, long-range correlation, although weak. And then you can plot this in color plot. So I discovered that the residues were anti-correlated. Namely, if you find a residue here 3, it's very improbable that the next one is going to be 3. It's someone else, but not 3. So then you start playing with Q, and you find beautiful tiling of your room. I mean, you can make really a beautiful decoration of this. But the limit is incredibly simple. The limit is this. The limit says there is one probability to be the same residue and one probability to be different. Simple like that, permutation. Okay? So going to the geometrical picture I had, there is indeed one way to remain on the same line, but there are q minus 1 way to go wherever you want. Okay? Simple like this. At this point,
I had the formula. So they really count what are the pair which differ by kappa and what are these numbers. And they provide formula, explicit formula, in which, notice the structure of this formula. The structure is very amazing. The structure is, there are indeed correlation, otherwise the probability would just be the product, it will be just the dimension of the group. There are correlations, so this extra term, but these terms are finite size effect. What physicists call finite size effect means each time that you have a material, no matter how large, there is going to be finite correction. But if you extend to infinity, there are no longer. So each time that I restrict my analysis to the first n prime, I get a correction. But if I take n goes to infinity, this correction is going to be killed. Okay? So there is a finite size effect which are ruled by anti-correlation if they are equal, or plus correlation, or to say positive correlation if they are different. And at this point, given this formula, you can compute everything. Asymptotically, there are no correlation at all, which was what I was experienced. So essentially, this series grows like a Brownian motion. But I have to be a little more precise on that. So to grow as a Brownian motion, I have to find that the variance goes like n. Now, the subtle point is how the hell I'm going to define this average. My series is deterministic. The prime are there. I cannot change anything. I can count the next angle. So how the hell I'm going to define this average? And then I rely on something on finance that probably, I hope is correct. Let me say. So the thing is, I use the same series to define its own ensemble. Okay? Means this is the series I cannot change at all. Is what it is. If I keep going, the series goes its own way. But this is a very well-known problem in statistical mechanics. The problem is called single Brownian motion trajectory. And has to do with history of physics. Namely, this is a very common problem on data analysis, biology, weather, stock market, and this and that. The problem is, in all these cases, you can never go back in time. So you can always go ahead, knowing what is before. But you cannot repeat the experience many, many times. So this is really related to what Jean Perrin did at the very beginning of the century. When he proved the Einstein number, Avogadro number, he take an ensemble average. So he made many, many, many Brownian motion, and he make an average on that. But later, Ivor Nordlund made a completely different experience. He take a drop of mercurium and just leave it in the water. One single trajectory, one. But then he did what? He takes snapshot of this Brownian motion. Okay? So, technically speaking, you are inverting average on the phase space on time average. And this holds as far as your stochastic process is ergodic and translation invariance. Okay? That is indeed what I somehow established. Namely, the ergodicity is clear because it takes all possible residue. The stationarity is less clear because the Dirichlet tells something in average, but you can check that is absolutely stable under any translation of the things. So at this point, using this, I use my own series to create my own ensemble. Namely, I cut it. And I cut it in many, many different times, how many times I like it. So each time I cut it, I have an ensemble. Each time I cut it, I have an ensemble. So I define block variable, the sum of the variable within one interval, which is enough large but small with respect to the total one. So like statistical mechanics. And therefore, if the original series goes like square root of n, any subset should go like square root of L. Okay? Is it true? Well, you can compute the variance explicitly. So this is the formula, the analytic formula. And notice that this formula has cancelled out completely the Q dependence. Is valid for any character. Q gone. At this point, I have a variance which goes like L, Brownian motion, with logarithmic correction. But logarithmic correction are mine. I don't care. They don't spoil the singularity. So then this has also a finite size effect, which means each time I analyze a finite sample, I have to take care, otherwise I make a mistake. But theoretically, if I go to infinity, I have perfect Brownian motion. Okay? So this is the things independent of the modulus. Can you check it? So I'm some Thomas. I try. I check it. Say, is possible? Let me see. So I take around 100 millions of prime, and I start doing statistics, changing the modulus, changing the character, changing everything. So I take key 2 of modulus 7. I found this perfect straight line. I take another one, modulus 11, another character, perfect straight line. I take another one, modulus 17, perfect straight line, with slope 1. I take another one. So obviously the error that you see in this plot are due to my ensemble, because I really have a statistical average to do. So I take another one. So this, of course, is increasing the error, because given the same number of prime, if I count in module 23, I have less statistics. But the slope is absolutely stunning. So if you plot all on top of the other, universal curve, a universal Gaussian, with distribution test which is exceptional. I bet with you that if you generate randomly number and check the validity of Gauss, you find worst values, amazingly. So this seems to be an even better way of generating random number. So then you might ask, okay, you have done all these analysis at finite n, but you have concern with infinity. How do you know that something fun is not going to happen later? No, because each time that I increase, even better. Because if I do statistics on this ensemble, and I found already a beautiful result, if this I insert in a larger things in which this becomes just a block variable, and this is the larger one, obviously it's going to be better, much better. And indeed, I made the finite size scaling, and the things goes precisely the way how it should go. So this is how the things is gone. And therefore, let me go back to the things. So the logarithmic of the L function was my indicator, which tell me where the first zero is going to show up. The first zero is going to show up relating to the growth of this density. And as far as this density goes like 1/2 plus epsilon, epsilon is the logarithmic, then you can conclude that the integral is singular sigma 1/2, and therefore all the zeros are on the critical line. Okay? So this is the line of thought. So let me jump to the conclusion. So there are indeed infinitely many functions which, as a Riemann, has all the zeros on the line 1/2. The property is largely independent of the primes. This is nice to underline, because many people immediately link this to the prime themselves. Is broader, the things. And this actually can be traced instead to some random properties of the prime. The validity of this generalized Riemann hypothesis essentially, I mean, in my view, rely on probability theorem, which involve residue and weak correlation. Namely, you can have a normal law distribution also with correlations as far as they are weak. And this is precisely the case. And the random walk theorem presented here is based essentially on 2 pillars, let's say. One is a theorem, is the Dirichlet theorem, which tell me the equidistribution of residue. And another one is this finite size correlation that were studied originally by Hardy and Littlewood and make it quantitative by Olivet and Sundararajan. And with this, I finish. Thank you very much.
Thank you, Professor Mussardo, for this fantastic talk. And perhaps we can open for a few questions now. So if anyone would like to ask a question. Hussein, just a second.
What would be the next class of L-function you would consider after Dirichlet L-function?
Well, as I said, here today I focus on the Dirichlet function non-principal character because we're entire, and so I was not stopped from the zeros. So the next challenge is really to prove for Riemann itself. I mean, to prove it. Prove is probably a too big word. I mean, to have some result on that. So that is technically non-trivial, the way to do, but can be done.
What's the problem when you told that there is no pole?
Yeah, the problem is this. The problem is if I take the log, let's say, of Riemann, this guy is going to be singular in 1 and zeros. Okay? Now, all my things were based on the sum of cosine of the angle computed on the prime. And then I have to show that this sum goes like square root of n. This was the basis of my argument. But in Riemann, all the angles are zeros. So this sum doesn't go like square root of n, it goes like n with power 1. Is correct? Yes, because this blows up at the pole, which is in 1. So what you have to do is technically subtract the driven, because this random walk is going like this. Subtract this driven part, take it out, something like, I know there is a pole. Can I know something about the zeros? But then you have to subtract this part and see what is left as some Brownian motion property. It's not trivial. It's not trivial, but I mean, I'm telling you the main ideas and why it's difficult technically for Riemann itself and the principal character rather than for the non-principal character. Non-principal character, these guys blows up only on the zeros. So I'm not concerned with the pole, and I mean, technically it's really a simplification, I have to say.
So in the case of the principle, it's a Brownian motion with drift.
Essentially, it's like this, essentially.
With random drift, perhaps.
Yeah.
Okay.
Yeah.
I see. Alexei.
Thank you. So it was really very much interesting. So probably what you just answered is related to, you said that if you substitute primes by arbitrary numbers but
with the
rightly
same
distributed,
growth.
yes,
Yeah.
then the properties essentially do not change. So do you expect it for the zeta function itself?
Yeah.
It's
the same.
just the same idea.
Yeah, absolutely the same.
But for L functions, it's a theorem, right, or not?
Say it again.
But for the L functions, is it a rigorous result?
No, but also for Riemann. No, it's absolutely the same. I just presented for Dirichlet because, I mean, I have to present
okay.
Dirichlet. But Riemann is a special case of Dirichlet. It's when you take Q equal 2, and therefore there is only one character, which is the trivial one. So Riemann is really a special case of Dirichlet function. So if you prove it for general Dirichlet, you had automatically for Riemann. The only case you have to distinguish is what I said, is Dirichlet is essentially two classes of function. The principal character, in which there is only 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0 on the periodicity. And the periodicity is Q. So if you have Q equal to Q minus 1, there is no zeros. So the principal case, which present the pole in S equal 1, and all the other, which indeed are instead integer function. There are no singularity on the complex plane, and there are only zeros. But the theorem goes exactly the same way. Yeah. Actually, it's very interesting. I have to specify something which is, I found personally very, very deep. these zero are really related to randomness. Namely, if you take a series of functions, a series of numbers, which are deterministically like n log n, which is how the prime goes, the zero gone. It's amazing. There is another theorem by another person that says, if you take now zeros, which goes like n log n, so really deterministic, no randomness, and you put in it, and you say where this function is going to have zeros, gone. There's no longer zero. You can prove it rigorously. So you infer that the zeros of this function appear just from the property of randomness. Actually, it's a very simple theorem of probability. The theorem of probability is if I define a function which I call, I don't know, A of S, which is a Dirichlet function, Dirichlet series, sorry. I'm not implying anything about infinite product, nothing. But I take these guys to be plus and minus 1 randomly distributed. So I have really a random function. Theorem. This function has singularity on the line 1/2. It's a theorem. Okay? So it's based really on random properties. So in the case of Dirichlet, if you take sequences which grows like the prime, I mean, it has to grow like prime because when you take the ratio, you want to have not zeros of the ratio. This is the only thing, essentially. But then it's necessary they fluctuate it. And they have to fluctuate it to produce the zeros. And it goes in that direction. I mean, you can construct yourself function which has singularity wherever you like, as far as you tune the randomness property of this coefficient. It's really a theorem. Okay? So in the case of Riemann, it's not random. I mean, this problem is deterministic. But what I try to argue today is that it's true it's deterministic, but at the end of the day, it's as much random as you like it. Indeed, you can do the following. I mean, there is something weird with probability. I mean, I found myself completely confusing. So, for instance, if I study this residue, modulus q, so means it's a set of number like if I take q equals 7, it's like 2, 3, 5, 4. Take it as a strip. Take this number and try to make any sense of it. So where it come from? Imagine I don't tell you where it come from. Well, you just analyze statistically, you really find, you find teeny correlation, but really which goes away as far as you enlarge. Now, the things which make me really, this conflict, deterministic and think is, imagine I drop a coin and I sign all the output. I sign it, all. But you have never see what I've done, okay? Then you enter, and then I tell you, look, I have 1, minus 1, 1, 1, minus 1, 1. And say, well, come on, you are dubbing me, it's a random walk. No, it's deterministic series. I can tell you what the 100th term is, and you cannot change it. You see what I mean? I mean, it's very, very confusing. I mean.
Perhaps one final question. Well, I have actually a final, or perhaps one, not final question, but one question more. So you mentioned this fitting of the Gaussian. Question is, have you tried other statistical tests? Like p-values? And
I found all, I mean, I analyzed in deep detail all this. I had the entire, under control the goodness of the fit,
Perhaps one further connection, just by chance. We have here Professor Venceslau Gonçalves Manteiga, and from statistics, and Professor Manuel Febreiro. And I wanted to mention that they study deeply the issues of resampling. And in a certain sense, what you are using in your test is this idea of resampling, of taking samples from this one single time series. And so perhaps there is...
Indeed, I mean, I'm naive on the field. Just to make clear, I'm not coming from from the mathematics field or random series or whatever. I took inspiration by this work done by this Ivar Nordlund, this guy that make one single shot, and he got Avogadro number with precision less than 1% in 1933. So just to make clear what I'm talking about. So this means that if you are able really to set up your cluster, making the series self-averaging itself, and you do properly, you have essentially defined your own cluster, I mean, your own ensemble, sorry. Yeah.
Okay, fantastic connections. Very nice talk. Thank you very much, Professor
Thank you.
Mussardo, once more.
Thank you.
Thank you.